Alright, I've got two examples here of applying the discrete-time Fourier transform properties. So let's look at the first example. We're going to consider the LTI system whose impulse response is h of n, which is given, and input is x of n, which is also given. Find the output by directly convolving in time and transforming to frequency, multiplying, and transforming back to time. So what we've got here is this x of n signal coming in, going through a linear time invariant system, which is just delaying by 1. You put in an impulse, this is the impulse response, put in an impulse, and the impulse just gets delayed by 1 unit. So that's our system here. We've got a delay. And then we're going to output, and we're looking for y, right? So here's our block diagram. So we're going to directly convolve in time, which is good, just to kind of refresh. So y of n is x of n convolved with h of n. So remember, this always applies. We're talking about frequency now, but the first half of the course we did the analysis in time. The output of a linear time invariant system is always the input convolved with its impulse response. So this convolution is very simple to do. We've got the impulse, which is delayed by 1 unit. I guess let me back up. X of n is this 1/2 to the n u of n, and then we're convolving that with delta of n minus 1. Now, convolution and the impulse function, the impulse function is your friend when it comes to convolution. It's like the identity. When you convolve something with the impulse, you get back the same thing. When you convolve something with a shifted impulse, you get back a shifted signal. So we can do this convolution very quickly without any diagrams or anything. This is 1/2 to the n minus 1 u of n minus 1. And that makes sense because we said this was a delay system. So if you put in 1/2 to the n u of n, then you get that same signal out, just delayed by 1 unit. So that would be the answer to A. All right, let's look at B. Transforming to frequency, multiplying, and transforming back to time. In this example, B happens to be the longer of the two parts. Okay, usually you have the option convolving or multiplying in frequency. When the convolution is dealing with impulses, then you probably want to convolve. But we're going to do both just to show you that they are the same thing. So when we convolve or when we multiply x, first we need its transform, and so there's a pair in the table, right, of common Fourier transform pairs. So this is alpha, 1/2 alpha to the n u of n. So that has a frequency, a Fourier transform 1 minus 1/2 e to the minus j omega alpha, right? 1 minus alpha e to the j omega minus j omega. So we've got capital X right there. We'll call that capital X of e to the j omega, and then the impulse response of this, or the frequency response, or the frequency response is the Fourier transform of h. So let's get that guy. So let's actually find it using the Fourier transform equation, right? So this is the sum of h of n times e to the minus j omega n, where n goes from minus infinity to infinity. So what is that? Well, I put in the delta function in for that. This is the sifting property of the delta function. So make sure that you're up to speed on that. When I put the delta function there, the only non-zero value in the summation is when n is equal to 1. So that sifts out e to the minus j omega when n equals 1. E to the minus j omega. So that's the frequency response, just that. So now we've transformed to frequency, right? We've transformed h to frequency, we've transformed x to frequency. Multiply those two together. So let me multiply them. So I've got e to the minus j omega times 1 minus 1 over 1 minus 1/2 e to the minus j omega. Okay, now we've got to, so this is y. This is the Y spectrum. So now we have to inverse transform that. Well, do you remember the time shift property? The time shift property says that x of n minus n0 has Fourier transform e to the minus j omega n0 times capital X of e to the j omega. So that looks like what we have here in frequency with n0. If we form fit, n0 is 1, and then we know the signal whose transform is this. We know x, right? And so when we inverse transform this from the time shift property with n0, it seems to be 1, we get back 1/2 n minus 1, right? We're going to shift by 1, u of n minus 1. And, that's our answer right there. That's the same thing we got up here. All right, feel free to pause that, but we're moving on. And this is actually, the second example is one of my favorite examples. We're going to consider this block diagram, and it says that each low-pass filter is ideal with cutoff frequency pi over 4. And so find the overall frequency response. So we'll call this guy EX, capital X, e to the j omega, and we'll say that has a transform of that, and then we'll say that this guy has a transform y, capital, and e to the j omega. And so what we're really looking for, remember block diagrams, we're considering this thing as a one big old system, and we want to find the frequency response of that system, right? And remember, I guess before that, from the convolution property, the output spectrum is the multiplication of X's spectrum with the frequency response. That's the convolution property. All right, and so we want to get the ratio of those two spectra, the output divided by the input. Can we do it? Right. That's the case. That's what we're looking for. Okay. So we're going to talk about these intermediate signals in here. So let's call this W1 of n. Okay. Let's call this W2 of n after the low pass filter. Let's call this W3 of n and W4 of n down here. All right. So notice, let's talk about W1 of n. So W1 of n, we'll probably run out of space eventually, but we'll go for right now. W1 of n is x of n times -1 to the n. So -1 to the n can also be written as e to the minus j pi n, like that. Or positive if you like too, it doesn't matter. So why is that? Well, I encourage you to plug in values of n. For example, e to the j pi, when n is equal to 1, that's -1. Then e to the j pi 2, so 2 pi, that's 1. Then -1, then +1, and so forth. Think of the complex plane. So that's W1 of n. So when we take its Fourier transform, W1 e to the j omega, well, what does this have an effect of doing, right? That has the effect of multiplying by a phasor in time has the effect of shifting the spectrum of X. So that is the frequency shift property. So that's W1 spectrum right there. It's just X's spectrum shifted up by pi. That's interesting. Okay, so now what is W2's spectrum? Well, W2 of e to the j omega, and this is the convolution property, is the out is the it's the output of the low pass filter. So that is E x of e to the j omega minus pi, right? That's what we put in. That's W1 spectrum times the low pass filter frequency response. So we'll just call HLP like that, or maybe we'll just show the independent variable of e to the j omega. So that's the spectrum of W2. Now, let's talk about W3. So this is getting longer now. So the spectrum of W3, well, we're again multiplying in time by -1 to the n. So that has, as we've talked about from the frequency shift property, that has the effect of shifting the W2's spectrum up by pi. So what I'm going to do is I'm going to take W2 spectrum, which is x times h, and I'm going to shift it by another pi. So now the x has been shifted by 2 pi, and the low pass has been shifted by pi. Okay, so that's W3's spectrum. So we've got that. Now let's talk about W4's spectrum. W4 spectrum is no big deal. W4 spectrum is x's spectrum times the low pass filter. So this is x e to the j omega, right? X's spectrum times the low pass filter. Okay, now let's look back at W3. I'm going to write down here W3 e to the j omega. So something interesting happens here. Remember that for discrete time Fourier transforms are periodic with period 2 pi. So when I shift x's spectrum by 2 pi, I get back x. So this is actually x of e to the j omega, right? The original spectrum times the low pass shifted by pi. Okay, and then so that was W3, and then we add to that W4, which is here. Okay, and so that would give me the output spectrum. Right? So now I can take x, I can factor it out, I can divide by x and get the ratio of y to x. So it looks to me like y to x is, so again, factor out x, divide by x, it looks like it's the low pass filter shifted in frequency by pi plus the low pass filter. You say, okay, big deal. So this is the answer. Find the overall frequency response. There it is. So big deal, right? What is that? So I'm going to delete the top example. And I want to plot this. So here is the ideal low-pass filter. Here's omega. The ideal low-pass filter looks like this, with cutoff frequency pi over 4, right, minus pi over 4, 1, and then it's periodic with period 2 pi. So here's 2 pi, here's minus 2 pi. This is the low-pass filter. Okay, so now what happens when we take what happens when we plot this guy? So we've got the low-pass filter. Okay, here's this term here, the low-pass filter. So we still have something like this, pi over 4, minus pi over 4, and then at 2 pi again, right? It has to be periodic with period 2 pi. It goes on forever. So that's this term here, right? That's the original low pass. Then we take this low pass and we shift it up by pi. So now we've got something that looks like this, pi. So what type of filter is this now? Well, it passes the low frequencies here, right? It passes the high frequencies as well, right? Pi is a high frequency in discrete time. So this is called a band stop filter. Band stop filter. And its job is to attenuate or stop the frequencies that fall in this range. Interesting. You see, so by just by using the code, if we coded up a low pass filter and then instituting these -1 to the n's, then we can create a different type of filter, a band stop filter from our low pass. And by the way, how do you institute -1 to the n's? Well, for even samples, this is 1, so x of n is unchanged, and for odd samples, this is -1, so it's flipped. So all you do is you iterate through each sample of x, and on the odd samples, you flip its sign. That's it.